Um, Week went by fast, right? I don't think I'm gonna have a practice test ready for you in time. So I think what we'll just do today is review these questions that I've given you in those Word docs. Just work those. If you've got questions on those, ask me today or ask me in an email tomorrow, and I'll try to give you a decent answer to it. I think other than that, my only announcement to make. The printer is not working, so I don't have a sign-in sheet. Hopefully I can find a way to print this afternoon's lab for you guys. I'm not sure what we'll do, but we'll work around it somehow if I can't print those. But apparently that printer is completely broken. It's not something minor. So I'm just going to go back over these. I guess I want to write them down so I'm not having to look back and forth. Tried to print them. Of course I couldn't. Starting with these.
The only problem is that we.
So some from chapter 6, starting with 6.55. Double check this. I guess that'll work for today. And again, y'all try to keep an eye on that. If it stops running, I will start by going 1, 3, 1, 5, and there's actually here. That's one has 2 has 2p. This one is. That one's 3D. Separated by color. So that would be a good reference for this section. And then there was these formulas. There's the 4 quantum numbers. There's n. So these are n. This 1, this 2, this 3, this 4. Those are the n's. And they just go in for their possibilities. It's 1 to infinity, I guess, but usually we stay in the low integers for this. There's L. The L numbers, like here I'll list these. That's 0. And then in level 2, this one's 0 and this one is 1. So those are 1. And then up here, this is 0, 1, and 2. This starts over as 0 for the 4th level. So that's the L number. You have M sub L. If I wanted to put those in, 0 in the middle. Wish I had another color. And then this one over here is 1, 1, 1. This one here is -1, -1, -1. This one's -2, +2. So those are the L numbers. And the last one is the spin number. And that one's always 1/2 or -1/2. The electron pointing up is 1/2. The electron pointing down is -1/2. L numbers go from 0, from L numbers 0 to N. So if N equals 1, this is the N number. Then it goes from 0 to N minus 1. That's what it is. So it's only 0. If you're in the 2 level, then you can have a 0 and a 1. So it's 2 minus 1. So 0 up to 2 minus 1, 1. So you've got a 0 and the 1. And for the L numbers, it's -L to +L. So if you're an L number 1, you go to L number 1, the M sub L is 1 to -1. Here when it's L equals 2, then you go from -2 up to +2. Anyway, you can draw this. I think you can get the answer from there. But I'm looking at 6.55. What are the possible values of L when N equals 4? So we're looking at this equation. 4 minus 1. So L equals 0 to 3. So the answer is L equals. So we're in this 4th level, we have S, P, D, F. So you would have 4 of these. In the 3 level, we have S, P, D, which is 0, 1, 2. I like to write this when it comes to L. If you understood that, if you understand the letter designations, the S's and the P's and the D's for this, then you can translate directly to what L is for any given orbital. So for that should be the answer to that one. That's A. If L equals 2, what are the possible values of M sub L? So if L equals 2, you got -2. Those are the possible values of M sub L if L equals 2. Here is where L equals 2. And you see -2, -1, 0, 1, 2. So that's what this is showing. What else here? So if ML is 2, so in a case where ML is 2, here. What are the possible values of L? It just has to be 2. That question seems backwards to me, but I wouldn't ask that one on. So consider A and B here and not C for what to look at for the test. Next I have 57. Give the numerical values of N and L. So so if we are, what did I say, 5, 7, 3p, there's the 3p. So they want N and L. So for 3p, N is 3. We're in the 3 level. So in that case, N equals 3. L, these are the L numbers. These I've got out to the left. So that will be a 1 there for L. So that's the answer to the first one. Those are the first 2 quantum numbers. So it's 3 and 1. If I said M sub L was 1 and MS was 1/2, I would be talking about the electron right here pointing up. So the M sub L is referring to these 3 numbers here. And I chose one of them. I chose the number 1. And I did plus 1/2. So the arrow is pointing up. So this particular electron, those are the full 4 quantum numbers for this particular electron. We're really covering orbitals up to here. And then we're covering the spin here. You guys okay with this? 2s or F. S for F, 5D. They're only asking for N, L, N, L. Two S, that means N equals 2. 4F is 4, 5D, 5. S's are zeros, so this is 0 for L. F is 3, D is a 2, that's all it is. A, B, C, and D. So for that one, A, B, C, and D. That was 6.57. Give the NL and ML values for each orbital in the 2p subshell. So that's 5, 8. Is that on the list? Yes. So 5, 8. So now they want NL and M sub L for each orbital. In the 2p subshell. Here's 2p. So N is 2. L for the p's, it's 1 for L. And then we'll have, these are the orbitals. That line, and that line are the orbitals. So there's 3 of these. I'll do this one. And then so this is the first 3 quantum numbers for that orbital. This is the first 3 quantum numbers for that orbital. And the last one, this one, N equals 2, L equals 1, and L equals -1. If I did the last quantum number, I'd be talking about whether I'm referencing an electron pointing up or an electron pointing down. But that's it. That's the 3 sets of the first 3 quantum numbers for the 2p. Is that what I just did? 2p. Each orbital in the 5d subshell. I don't have that picture here. We could continue to build this up to the 5D, but there's a lot more layers to add there, but if I say it's 5D, all right, D's, this is 3D, but the 5D looks just like this. 1, 2, 3, 4, 5, there's 5 orbitals there. So if I was doing the 5D, and that's the first orbital, the second orbital, the third, the fourth, and the fifth. For one thing, n equals, these aren't quantum numbers, these are just me numbering the 5 orbitals across, but n equals 5, n equals 5. If we're doing 5D, n equals 5 for all of these. If it's a D, then the L number is a 2. All right, now we start differentiating, and L equals. We're going to have a 2, a 1, a 0, a -1, and a -2. There's the 5 sets of the first 3 quantum numbers for a 5D orbital. You guys okay? It's abstract, but it's not that hard. It really isn't. Where are we? 6.2. 6.62. Okay, this is a black one, black numbered problem. And y'all didn't have answers to that. Did I give you? I just like that question, but it didn't have. It didn't pair with anything. All right, but let's go through these. N equals 2, L equals 1. So they're giving the first 3 quantum numbers. And the first example here is if it was 2, 1, -1. It was 2, 1, -1. We look here first, and that locates us here. L equals 1. We're not at 0, we're at 1, so we're somewhere here in the 2p. Is that all they asked for? Yeah, that's all they asked for. The NL is the one you look at to help you decide if these are impossible or not. Maybe the L as well, but let's keep going. So yeah, 2p for the first example, 1, 0, 0. So n equals 1 means we're here. So there's the n equals 1, we're in this level. L equals 0, of course it has to because there's nothing else to do. Or L equals 0, that's the L. And it's 0, so this is possible, so the answer there is the 1s. For the second question there. So over here under orbital, it would be 1s. All right, 3, -3, 2. So where are we? Here's the 3. L -3. These numbers are never negative. That's what it has, right? So that one's impossible because you can't have negatives on the L. If you ask me, why can't you have negative L numbers? There's not really a good answer to that. This is just how the math works for the quantum equations that these numbers go into. But this just goes on. There is such thing as a g orbital as you get further up, and it would be 4. I think they just go H, I, J, K after that. 6, 7, 8. They never go negative. So S, P, D, F, 0, 1, 2, 3, and it just goes on. There was meaning behind these letters early on as they were discovering things about quantum mechanics. And then when they realized it was just going to go on and on, they just started with F and went G, H, I, J, K. So they were trying to do something with naming here, early days studying quantum mechanics. And they got to F, and that meant something, and then when they realized it was just going to go on and on, they just picked up with the alphabetical order with the alphabet and just kept going. But notice they all just go towards positive, so that's the problem with that one. So that one is impossible. So that can't be negative. The next one, 3, 2, negative 2. 3, 2. Okay, you can have negatives for n sub L, but let's look at it. We're up here in the 3, L is 2, so we're here. Negative 2, yep, that's possible. That's the 3D. This gives a little more detail outside of 3D. It identifies which orbital in the 3D. But we can look at that and help still decide whether this is possible or not. That's possible. If this had said 4 or 3 or negative 3, that would be beyond this list. Negative 2, negative 3, 2, 3. But that's possible, and that's the 3D. 3, 2, negative 2, 2, 0, negative 1, this one. 2, 0, negative 1, so we're here. 0 tells us we're here in this orbital. And negative 1, there's no negative 1 here. There's just 0. There's no negative 1, there's no positive 1, it's just 0. So that's impossible because of that. Negative L to L. Since L is 0, it's just going to be 0. So you can't have a negative L. So there's that definition as well. 2, 0, negative 1. 0, 0, 0. There is no such thing as n equals 0. The n quantum numbers start with a 1, and then go to a 2, and go to a 3. So this one just starts out impossible because there is no n equals 0. N has to at least be 1. 4, 2, 1. All right, we're in the n equals 4 level. L equals 2, so we're in the D. So we're in the 4D. I'm looking at this now to decide whether it's possible, and it is. We're in the D, so we're in a 4D. It looks just like this, except it's up higher, and this would be a 4. But there is a 1 as an M sub L number. So that's possible, and it's a 4D. So maybe that helps illuminate these. 50, 62. 71 on the list. Maximum number of electrons that can occupy each of the following subshells. As far as nomenclature goes, this, because this is where all the 2's are, n equals 2, there's none up here, that's a shell, and then this S is a subshell, and this P is a subshell. And then each line is an orbital. So this is saying number 71, maximum number of electrons that can occupy each of the following subshells. So 3P, we're actually done with the questions that deal with these quantum numbers. I'm going to get those out of our way. So we're literally just using a different way to refer to the orbitals now. We're just going to stick to these. Don't need that stuff. 71. 3P is here. How many electrons can fit in this subshell? 6. Two per line here. You get a pair of electrons in each one of those orbitals. 5D, this is 3D, but 5D looks just like this. How many electrons fit in here? It's 10, it's 2 per, and there's 5. 2S, how many electrons fit here? 2. These should be obvious. F, So there's s orbitals are 1 line, p orbitals are 3 lines, d orbitals are 5 lines, f orbitals, guess what, are 7 lines. So you're literally just going by odd numbers. So I have 7 here. How many electrons can fit there? How many? 14. You don't start running into f orbitals until you get to at least n equals 4. 0, 1, 2, yeah, it would be the 3 on the L. So 4 and above can have f orbitals. There's 1 line for this, 3 lines for this, 5, 7. How many do you think there are for G? 9. And how many for H? 11. It just goes on like that. It's odd numbers. So there is actually a pattern here. It's just a little bit obscure. What else I got? 72. Oh, we're back to the quantum numbers. I shouldn't have erased them. Maximum number of electrons, you have the following quantum numbers. N equals 3, and N sub L. Oh, they can have these quantum numbers. M sub L, well, I'll just note where it is. N equals 3, meaning we're in one of these purple ones. Because these are the 3s. M sub L is the 3rd quantum number. So I'm saying N equals 3, L equals, we haven't decided, M sub L equals -2. All right. So the L numbers are 0, 1, 2. And we haven't specified what the L is. It's just given us the N and the M sub L. But if I filled out the M sub L numbers all through here, it's a 0 there, a 0 there, a 0 there. It's 0 in the middle. If you have a line to the right, it's a 1. Line to the left would be -1. And then this one has 2, -2. And it's saying M sub L is -2. That means we have to be in here. That means we have to be in the 3D. So now I can go here and go 2. Because this is -2. This has to be at least 2. And since this is 3, that's really the only place it could be. If it was N equals 4, then there would be, this was 7, and this would have a -2, but it would also have a -3. So there would be 2 of these in the 4 level because it's got that orbital. But since we're in N equals 3, and this is -2, but then this has to be 2, and we're necessarily in the 3D. Okay. And the question is, maximum number of electrons. So all the electrons in the 3, oh no, it's only these 2. So only as many as 2 electrons can have that full. What's the next question? I guess the mere fact that this was specified, you knew it was going to be only 2. Merely because this was specified. As soon as you name something in M sub L, that's this addressing. And you can only get 2 there, so as soon as we saw that -2, I should have just said 2 electron is the maximum that can be there. That's what it's asking, right?
Yeah.
Yeah, it can have the following quantum numbers. Do you have a question?
Yeah, if it was N equals 4, would it be 4 electrons?
No, you would still have, yeah, you're right. Let's see if one of these other ones do that. N equals 4, L equals 3. N equals 5, okay. Okay, let's just do B. N equals 4, L equals 3. All right, so that would be, if L equals 3, so here's L. If it's 3, we're in the F orbitals. So now we're in, now I want to draw these. But let me just draw over here. Somewhere above there. So here's the 4S that I've decided to label there. We'll do this in blue. Somewhere above there, there's 4P. Somewhere above there, there's 4D. And then since it's 4, now we have 1, 2, 3, 4, 5, 6, 7. So there's the 4S. Right above here would be the 4P, but I'm hesitating to put it on over there because more stuff starts overlapping. But somewhere above there, here's the 4S. Somewhere above there, there's this stuff. Right. So N equals 4, L equals 3. The L numbers are here. So when it says L equals 3, we're up here. Did it give an M sub L? No, it didn't. So how many electrons can have those two numbers? All the electrons in here start with those two numbers. So this is actually 7 times 2. So 14 electrons can start with those two numbers. Do you follow that? That's B. And I think C here will run into that weird problem she brought up. N equals 5, L equals 3. SPD. This was 4F. I should have had 4F here, the previous one, just for the continuity. But let me do this. Now that we're in N equals 5, now we actually have, that was 7. So now I need to draw 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it says N equals 5. L equals 3. That means we're here in the 5F. And then it says M sub L. No, we don't run into that problem. M sub L is 2.
You got rid of the L. Just pretend the L's not there and then do.
Yeah, then we would have that problem.
Yeah.
Yeah. M sub L is 2. So that tells us we are, these are 0. 2, U, 1, 2, 3, 4, 5, 6. Here, M is 2, so we're here. So we have all that, so we've addressed our way down to here. We can have 2 electrons that can have those 3 quantum numbers. Because we're specified all the way down to this point. Since I build tests from the questions I give you, and this one doesn't seem to be doing that. If they didn't give us the L number here, then any of these that have a 2, this one has a 2, this one has a 2, and this one has a 2. For the M sub L, if this was not given, that would mean there are 6 electrons that can have an n equals 5 for the first number and ml equals 2 for the third number. Then you can have 6. You see that? I won't ask one like that on the test because it's not in the questions, but that's what she was saying. N equals 4. So for D, for 6.72, N equals 4, L equals 1, ml equals 0. That'll be 2 electrons. Because this was specified and this was specified. Right? That's right. It's 4, so if we were 1, 2, 3, 4. That last one is saying N equals 4, L equals 1, ML is 0. F, L equals 1, ML equals 0. So it's pointing right here. So you could get 2 electrons in there. One of the points of these quantum numbers, if I added an m sub s and I decided I would do -1/2, pointing down, a full set of quantum numbers, only 1 electron in any atom can have the same set of quantum numbers. Any set of quantum numbers, full set, all 4, specifies only 1 electron. That's kind of the point of these numbers. They specify down to 1 particular electron. And the utility in these is in complicated quantum mechanics equations. You can use that full set of numbers to find out all kinds of things about that particular electron. Its angular momentum, its energy, various things. Its shape in space, the orbital itself. And we do use those. We'll get to these in just a little bit. Remember an equation like this. Squared final. These n's, there's the quantum number. But this is one of the more simple equations, and that's as far as we go. But this is an example of one of those quantum mechanical equations that you can use these numbers for. But we only specify wavelengths and what else? Energies. And we're always in the n equals. I mentioned kind of in passing that these types of equations really only work for these. This type of equation. And remember that this is 0 and this is 0. 0. 0, 0. Those do get plugged into the quantum mechanical equation, but since they're 0, you multiply by 0, parts of this equation just go away when you're dealing only in the s orbitals, because these numbers that you would plug in, if that's 0 and that's 0, those parts of the equation just disappear and we're stuck with just this fundamental one. But we won't do any more complicated ones than that. You would take some physics class, and in chemistry, you'd be taking a physical chemistry class if you were a chemistry major to get further into those kind of equations. And then you see really why this game we're playing here is useful for anything. What else? That was 72. I just have to worry about time getting through all these. 74, 6.74, indicate the number of valence electrons, core electrons, and unpaired electrons in the ground state of nitrogen. So here is where doing this is useful. Now I think we're done with those quantum numbers. So you construct this, these lines the way I've got them. Just get the quantum numbers out of the way. All right, nitrogen. It's saying ground state and it's not indicating charge. So same number of electrons as there are protons. You look at nitrogen, how many protons does it have? If you're looking at the periodic table, 7. That's what that 7 means. But for the neutral atom that we're dealing with, that means it also has 7 electrons. And then you do this. If you've got this constructed, you go up to 7. 1, 2, 3, 4, and now I go across 5, 6, 7. If it was more than 7, I would be coming back and starting to pair them as I counted. That's 7. That's the electron configuration of nitrogen. Core electrons and valence electrons. If I ask you how many valence electrons there are on nitrogen, and I stood in front of this and you looked at the periodic table, what would you tell me? Valence electrons. You just count over to the left.
Oh,
5. You look at nitrogen, you count nitrogen, and you count to the left. 1, 2, 3, 4, 5. Count out to the left end, there's 5. That's a quick way to get valence electrons from the periodic table. But what that's telling you is the valence level is the n level, quantum number n, the highest one that has electrons in it. Notice the 3 level and the 4 level and the 5 level don't have any. So we just ignore those. The valence electrons are there for the ones in the 2 level, and there are 1, 2, 3, 4, 5. So if you want to see valence electrons not on the periodic table but on this chart, it's these. These are the valence electrons for nitrogen, and there's 5 of them. What's inside here are the core electrons. So for nitrogen, there's 5 in the valence, 2 in the core. Total of 7. And how many unpaired electrons? 3. Something else we talked about, if I just want to allude to it real quick. I told you about Lewis structures. You'd get the number 5 from the valence electrons. You'd go 1, 2, 3, 4, 5. And you're literally looking at 3 unpaired and 1 lone pair. There's the pair that's together, and that these 3 are these 3. So those two ideas totally overlap. I think y'all can do those. I think I need to move forward though. I think we'll have all the time. What was that, 4.74? 74. Of these condensed electron configurations. There's this other way of indicating electron configurations. I don't even think my Christmas tree form here, this kind of looks like a Christmas tree going up. Modern books don't use that, but that's just the key to me. That's the only way to do this. But they have you do this. Most books have this other way. So the 1s has 2 electrons in it. 2s has 2 electrons in it. And then 2p comes next. And that's got 3 in it. So that's another way to write the electron configuration. And one more thing you can do, you can take the noble gases. So helium, that's the electron configuration for helium. That is, if you did helium and it has 2 electrons in it, you would start, you would go 1, 2, electron configuration of helium. Another way of showing the electron configuration of helium. And then you can use that here and just say helium. That didn't really, this is the condensed electron configuration. That doesn't help much for something as small as nitrogen. But if you had, let's say, nitrogen, go all the way up to here. Sodium, so that's the electron configuration of sodium. These are the core electrons. It only has one valence electron. And this one would be 2, 4, 6, 2p3s1. So if I just counted those going up, I'd be doing this. But now you can see where it gets useful, where you can go, and you don't have to write all of this, because all of that is the electron configuration for neon. So that's the condensed electron configuration going this way. And I'll specify on the test how I want you to, which form I want, but be able to do both. What was that, 75, 76. So 75 and 76 are the same. Got 77 and 78. So 77 you have the answers to. So all right, this N here, they're not specifying it. They're just saying this particular atom has 2 electrons in the s and 5 electrons in the p orbitals. And then there's some noble gas configuration you could put here. Oh, I didn't bring my laser pointer. But if you've got 5 in the p orbitals, looking up there at boron, 1, 2, 3, 4, 5. So fluorine, chlorine, bromine, iodine, just going straight down this column. All of those could be represented by that first formula. This. They would all have some number S2, some number P5, and then some noble gas written in here. You see that? That whole column, the halides, fluorine, chlorine, bromine, those could all be done this way. And as to N minus 1, N minus 1. Let me cross 78 off the list. That's just getting too creative there for me. And I will strike through. I want to, I'll come back for these if I have time, but let me move forward. That was going back to chapter 4 for titrations, since we were doing that in lab that day. I wanted to go back and get it. All right. 619. Is the camera still on?
Yep.
Awesome. One good video focused on the board maybe will make up for me not having a practice test for you. Okay. So we're going back towards the beginning of this chapter. 619, question 619. Oh, this is the way. I gotta write these down. 19, 20, 21, 26, 27, 28, 29. Okay. Let's look at those. these just come down to, let's not do that one. I'm pretty sure I saw this one the other day, but it's a good example, so. So you will want, I'll give you these equations on a sheet on the test. C equals, this is wavelength, this is speed of light. Speed of light is a constant. I will give you that on the test. That's 10 to the 8 meters per second. Nanometers per second. Beat that. 17, right? You'll have that in your notes. I want to double check that. 10 to the 8 meters in 1 second. And I want to change that to nanometers or meters. 10 to the 9 nanometers. That's right, 17. Wavelength is so frequently done in nanometers that it's useful to have that conversion already done for calculations. I'm not sure if this first question needs it. 19, 20. All right. 6.20. What is the frequency of radiation whose wavelength is 0.86 nanometers? The algebra is very simple. What is the frequency of? So I divide both sides by wavelength and I get this. Now to find frequency, I need that over what's given. 0.86 nanometers. So I have 0.86 nanometers for the wavelength. C is 0 times 10 to the 17 nanometers. Let me write it like this, just so the units cancel in the way that makes my brain happy. Nanometers per second. So I want to write it like that. Nanometers per 1 second. Nanometers. Frequency is 1 over seconds. Sometimes called cycles per second. Cycles per second. So all we're doing here is nanometers cancel, and we ultimately just have seconds. So all you do in your calculator here is 3 divided by 0.86. Two significant figures. Six. So what I would write next is that's what my calculator gives me. We're keeping two significant figures because of those two. That's 3 significant figures. The 8 rounds the 4, so I would end on 3.5 here. for the numerical value, and then times 17 100s. That's the frequency, 3.5 times 10 to the 17 cycles per second. What is the wavelength of radiation that has that as a frequency? Just notation-wise, realize s to the -1, they could have written this. S to the -1, that could also be written in s to the -1. Be 6.4 times 10 to the 11 per second. Over S. Again, this part is just simple algebra. So now we're solving for the wavelength and we're given the frequency. So with some algebra, this is what we're solving. Speed of light on top, this on bottom. I'm going to use nanometers per second. I think this will come out better. Does it specify? It says, what is the wavelength? So I don't have to use nanometers. I could use meters. I could use whichever measurement I want, but given the phrasing, and if you really wanted a unit here, you could say cycles. Most textbooks don't even include that. It just per second. Hertz means per second. Whatever seconds. No, that's not right. I want to end in nanometers, so.
So what you divide in?
Yeah. I could rewrite this as 6.4 times 10 to the 11, no unit over 1 second. But I'm going to use the inverse of that. So I'm going to put the 1 second on top. And like I said, the unit here would really be cycles. Here's a wave. The wavelength, you just pick a point, and here's the wavelength. So really, you can say wavelength, or you can say 1 cycle, because that's 1 full cycle. So this is the way I would solve this. That stuff cancels, and we're ultimately going. I've also got 10 to the 17 nanometers over 10 to the 11 nanometers. So equals. So I go ahead and cancel those. I shift this underneath here. I've got the nanometers there. So that's just easier to me. That'll do in my calculator. This I'm going to go, let's split this up. So I'm going to first get the numerical value I want. 3 divided by 6.4. To 2 significant figures, I get 0.47 times 10 to the, well, how would I do this? I'm going to move the 10 to the 11 up to the top. Let me go ahead and put nanometers down here. Once I do that, it's 10 to the -11. So 17 minus 11, 10 to the 6, 10 to the, 10 to the 6. 4.7 times 10 to the 6 nanometers. That's the wavelength. If you wanted it in standard scientific notation, it would be 7.4 times 10 to the 5 nanometers. Oh yeah. Nanometers, frequency. We're given a frequency, but for a question like that, I will give you, where is it? I'll give you this. That one, the frequency was 6.4 times 10 to the 11th frequency. So this is wavelength, and it's got, yeah, that's frequency. 10 to the 11th. .4 times 10 to the 11th. 10 to the 11th would be about here in the microwaves. So it was the first one that we calculated was down in the X-rays. But just be able to use this chart. I won't make you memorize it. Is that 25? That was 20. This is the same type of calculation. 621, 625. So I've got 625 and 626. I think I solved this one the other day too, but I'll do it again. 626. We've got a wavelength of 532 nanometers. What is the frequency? So 532. So finding the frequency. 10 to the 17 nanometers. 1 second. 532. Solve it like that. 3 divided by 532. I get going to have 3 significant figures, so 564. So 3 divided by 532, this is what my calculator gives me, rounded to here. Nanometers. So we've got 1/2. That's the answer. These, if you're going to use that chart, you have to put it in scientific notation or standard scientific notation. 1, 2, 3, that'll be 654. 1, 2, 3. That one should be 5.64 times 10 to the 14th per second. Cycles per second. Okay, energy of these photons. So now we are, let's see, frequency. We can use this equation along with the frequency and this constant to find the energy in joules. And now we got Planck's constant You don't have to memorize this. I'll give it to you on the test. And this one is in weird units. It's joule seconds. So joule seconds. All right. And we got this for our frequency. We're doing this right. Energy of these photons. Yeah. So B says, what is the energy of these photons? Now that we have this frequency, 5.64 times 10 to the 14th. Just writing that down so I don't lose it. I guess we could have. There's a way to fit these together, but, all right, yeah, right. That over 1 second. That's this rewritten this way. Planck's constant, joule seconds. Joule seconds. That's how to set it up. I will split the numerical values. So the seconds cancel, and now there's really nothing in the denominators, so I'm just going to rewrite this. 5.64 times 6.626, so that's this and this. Now I'm going to do 10 to the 14th and 10 to the negative 34. And then it's all that's left to write is J for joules. All right, so this part I'll do in my calculator. 14 minus negative 34, I should be able to do in my head, but I don't want to. What is it? 20? Negative 20? Three significant figures, 4, so I'm going to keep 3. I've got that, negative 20. If I do that, it's negative 19. So standard scientific notation. All right, and this is for one photon, one individual photon. All right, 532 nanometers. What is the energy of one of these photons? All right, the energy gap that created that photon from the laser equals this. So we have these energy levels. And the first question asked us, first question said that laser pointer is shooting out lasers. Green laser pointer, 532 nanometers. So it was saying 532 nanometers. And it said, so what's the frequency? So we used that to find the frequency. It was this. That photon had 10 to the 14. That is its frequency. And then we went one more step and found that that's the energy of that photon. So that gave us the wavelength, the frequency, and it gave us the energy. What that means some electron up here dropped down to the ground state, and the energy gap between here and here necessarily was this, because that's how much energy the photon had in it that shot out of it. So there's no calculation for C.
Wait, so when it drops energy levels, is that basically it's when it drops energy levels that's letting it release from the,
Yeah,
okay,
yeah.
that's what